Today's lesson is going to be covering GCF factoring or factoring out a GCF. So let's begin by talking about what is a greatest common factor. A greatest common factor is the largest possible factor that will divide evenly into a set of given terms. So it could be just a constant that we're factoring out if a number divides evenly into both terms, or it could involve a polynomial term, a constant, and maybe some variables with it. So let's look at some examples on finding greatest common factors. Our first example, we're just going to find the greatest common factor between two numbers, 12 and 18. So I'm going to begin by just listing out the factors of 12. So all of the numbers that will divide evenly into 12. So 1, 2, 3, 4, 6, and 12. These are all of the numbers that will divide evenly into 12. Let's do the same thing for 18. 1, 2, 3, 6, 9, and 18. Okay, in order to be the greatest common factor, it must appear in both lists and be the largest possible value. So I'm going to first circle any common factors, and then we'll determine which one is the greatest. So notice that we have 1 appearing in our list. We have 2 appearing in both lists, 3, and 6. Now, in order for it to be the greatest common factor, it has to be the largest of the commons. So if we look, we have 4 common factors, 4 numbers that are in both lists, but 6 is the greatest. So our GCF between 12 and 18 would be 6. It is the largest possible value that will divide evenly into both of those terms, 12 and 18. Okay, let's look at one that's a little bit more involved. It has some variables listed with it. So our first term is 24x to the 5th, y to the 3rd. And our second term is 40x to the 4th, y squared, z. So just like before, I'm going to list out all of the factors of each of those. So starting with the first term, the numbers that will divide evenly are 1, 2, 3, 8, 4, almost missed that one, 6, 8, 12, and 24. But we also have variables. So if we think about what x to the 5th would mean, we would be multiplying x times itself 5 times. So there's 5 x's listed out as factors. And then y to the 3rd means we're multiplying y times itself 3 times. So we have 3 y's that are also factors. If we do the same thing for 40, x to the 4th, y squared, z, our factors would be 1, 2, 4, 5, 8, 10, 20, and 40. And then variables, we would have x 4 times, y twice, and we also have a z. as a factor. Okay, so in order for it to be a common factor, it must appear in both lists and be the largest. So as far as numbers, it looks like 8 is the largest constant factor that we see in both lists. But we also have some variables that are common. So we have x's in both. The top list has 5, the bottom has 4. So only 4 of them are common, meaning appearing in both lists. That top one has an extra x, but the bottom one doesn't have one to match it. And then if we look at the y's appear in both lists. The bottom one only has 2. So that means the top common factor would be both of those y's. Again, we have an extra y factor in the first term. We have an extra z factor in the second term. But again, we don't have ones that match those. So as far as the GCF goes, we would have 8x to the 4th y squared as our GCF. So when it comes to variables, you want to pick the smaller exponent in order for it to be common. All right, we're going to be learning a process called factoring out a GCF. So guys, this is kind of like backwards distributive property. So our answers are going to look like a distributive property question. But we could use distributive property to check our answer to see if we did it correctly at any time. So let's take a look at our first example. We have 81z minus 45. So we would first think about what would be the GCF between these two terms, 81z and 45. So first of all, the first one has a variable. The second one doesn't. So we're not going to have a common variable in this one, but I do need to think about a common factor between 81 and 45. Me personally, I can think of 9 as the highest number that will divide into both of those evenly. So 9 would be the GCF. Once you find it, that is the term that is going to go on the outside of the parenthesis. And then we think 9 times what will give me 81z? Well, 9 times 9z will give me 81z. And then likewise, 9 times what will give us negative 45? 9 times negative 5 will give us negative 45. I could use distributive property to check my answer if I wanted. 9 times 9z, do I get 81z? Yes, I do. And 9 times negative 5, do we get negative 45? Yes, we do. If your answer is yes to those questions, we have our final answer of 9 times 9z minus 5. We have factored out a GCF of 9. All right, here's the next example. We have 9x squared minus 27x plus 18. So we're starting with a trinomial this time, and in order for it to be a GCF, it does need to divide evenly into all 3 terms. Notice this last term does not have a variable with it. So therefore, there are no common variables. So let's just focus on the numbers. We have 9, 27, and 18. 9 will divide into all of these evenly. So I'm going to pull out a 9 as my GCF. 9 times what will give me 9x squared? X squared. So 9 times x squared gives me that 9x squared. 9 times what will give me negative 27x? Well, 9 times negative 3x will give me negative 27x. And 9 times what will give me positive 18? 9 times a positive 2 will give me positive 18. Again, we could use distributive property to check. 9 times x squared, do we get 9x squared? Yes, we do. 9 times negative 3x, that does make negative 27x. And 9 times 2 does give me the 18. So we know we've factored out the GCF appropriately. Our next example says 25x squared y minus 20y. Notice that both of these terms have y in them. So this is our first example where we're going to have not only a number, but also a variable that's common. So if we think about those numbers, we have 25 and 20. 5 will divide evenly into both. And we said earlier that both terms have y in them, so we need to factor out that common y. Again, we think multiply. 5y times what will give us 25x squared y? Well, 5x squared times 5y will give me that 25x squared y. And then 5y times what will give me negative 20y. 5y times negative 4 will give me that negative 20y. Again, use distributive property to double check. 5y times 5x squared, does that give me 25x squared y? Yes, it does. And 5y times negative 4, that does give us negative 20y. So we are correct, and that is my factored form, factoring out that GCF of 5y. Okay, this next example, we see that there's 4 terms here. So it's a polynomial, we have variables, and we have numbers. So there's lots of things to consider with this example. So this is one of the more difficult ones. Let's take a look at those variables first. There is an r in all 3, and technically there's an r squared in all, 4 terms. There's 4 terms there, not 3. The s, there is an s in every single term, so the s is going to be common. But if we look, the t is not common to all 4. So we have r squared s as our common variables. And if we look at our numbers, thinking about a number that will divide into 56, 21, 70, and 7, I think the highest one is 7. So 7r squared s is our GCF. Now let's think multiply. 7r squared s times what will give me 56 r to the 4th, s to the 3rd, t squared. Woo. All right, so 7 times 8 is 56. We have r squared, so we need to multiply it by another r squared to get r to the 4th. We're multiplying s by s squared because we need s to the 3rd power. We did not factor out any t's, so we're going to still need that t squared on that term. Okay, the next term. We are multiplying 7r squared s times something to give me 21r to the 3rd s squared t. Well, 7 times 3 makes 21. R squared times another r would give me r cubed. S times another s would give me s squared. And we didn't factor out a t, so we're still going to have that t on the inside. 7r squared s times something should give me negative 70r squared s squared. So if we think about the number, 7 times negative 10 gives me the negative 70. R squared multiplied by nothing else because we need just r squared. So I don't want to multiply it by another r because I do not want to increase that power. But s times s would give me s squared. So I do need that s on the 10, negative 10 rather. The last one, we have 7r squared s times what will give me negative 7r squared s. That's a negative 1. Again, we could use distributive property to check our answer to make sure that we would get right back to what we started with. Okay, this concludes the notes on GCF. Make sure you watch the next video on GCF and grouping.